Welcome back, everyone. As you can see from the circuit that I've got up here on the screen, we are going to have quite a good day today. So this here is the build documentation for the Aeon Blue Shift, which is a clone of the Boss DC-2. The Dimension Chorus was a super popular 80s effect, a lot of times done in the studio on a rack mount unit, but adapted to a pedal format by Boss in the mid to late 80s. As you can see here, there is a whole lot going on inside of it. If you have not watched my video on the Boss CE2 yet, I highly recommend that you go watch that first, because there are some things in that video that we're going to kind of gloss over a little bit today, assuming that you remember them. And if you have seen the video and you just don't remember it very well, you may want to go back and reference it at some point as well. So the way that a dimension chorus works is that you have two chorus or two delay lines that you're modulating, and you modulate them out of phase with each other. If you remember our harmonic tremolo video, we took the LFO, we created an inverted version of it, and we used the non-inverted and the inverted versions to modulate the high frequency and low frequency components separately. The DC-2 is sort of like that, except instead of separating the audio into high and low frequency components, it splits it left and right, so that as you get a positive pitch shift on the left side, you get a negative pitch shift on the right side, and vice versa. And they're perfectly synchronized, so that when you hear the combined effect with the dry signal, it makes this sound that is often described as a stationary chorus sound, or a chorus sound where it doesn't really feel like it's moving, but there is certainly depth to it. And that is done because you're not taking a single pitch shift and wobbling it around. In fact, if you were to play with the LFO and make it super, super strong so that you're heavily modulating the delay time, with a dimension chorus, you don't get that really seasick kind of feeling. In fact, if you go look at my circuit, alternate dimension, it will function as a regular stereo chorus or as a dimension chorus, and the dimension chorus can be dialed in much more than just the switches on the Boss DC-2. Okay, with that introduction out of the way, we're going to break up our circuit into its individual components. For the signal path, we have all these various components here. And they look like, well, there's also all of this, and there is this. Okay, so these are all the signal path components that we have from in our DC-2. Okay, so those are the signal path components. The non-signal path components are going to be the ones dealing with the LFO and the clock driver IC, and that's going to be this whole big chunk here, which we will break down and go through a little bit as well. All right, so there is a lot of stuff in here, but as we break it down, if you've seen the video on the CE2 and some of the other videos, you'll see that it actually is more manageable than we might think at first. I'm going to zoom in here some. Let's zoom in a little more. And let's zoom in even more. I just want to make sure that we can see everything clearly here. Okay. So, we're going to start off with this first section. This is a very basic input buffer. Okay? It is non-inverting. unity gain because we have tied the output back to the inverting input. We have our input resistor, an input capacitor, our bias resistor that is biasing our positive terminal or our non-inverting terminal up to our reference voltage level. Okay? Easy peasy. That part, check, off the list. No need to dwell on it further. You will notice some of these solder pad points. Those are just for the specific implementation for the Aeon kit. We are going to treat these as jumpers, okay? So we don't have to worry about that. Next up is this stage, okay? This stage, if you remember from the CE2 video, we talked about how BBD devices are inherently noisy and they have high frequency noise. And so what we do is before we put our signal into the into the BBD, we boost the high frequencies so that the high frequencies are going to be much stronger than the high frequency noise in the chip. And then after we come out of the BBD device, we will then have a correspondingly matching filter that will then return the high frequency content back to its original level so that, you know, the input and output signals have the same relative frequency response, okay, or relatively similar frequency responses. So that is what this is doing, okay? It is a shaping filter or an emphasis filter, if you will. From there, we move on to this new component here that is the NE570 is what's called a Compander. And we're only using half of it here. We're using this part here. The way a Compander works is it has circuitry inside that will either act as a compressor or an expander. This IC was developed for use in situations where you have limited dynamic range. So you may have a source signal with lots of dynamic range, but you may need to do some processing with components that have a limited dynamic range. And bucket brigade devices, particularly ones with very long delay times, fit that description perfectly. They are devices that have only a certain amount of dynamic range that they can represent, and that dynamic range is represented by the level of charge that the capacitors inside of it can hold. And so in order to make it so that we don't saturate the BBD, which would result in distortion, it would be, so if we were to saturate the BBD where we are, you know, so if our original signal were to look like, you know, we have our charge buckets in our BBD that look like this, right, for this kind of a signal. If we were to saturate the BBD, we would end up doing something where we have something like this, where instead of having a source signal that looks like this, or rather, let me draw that a little better. Instead of having a source signal that goes like this, we would end up with an output signal that looks like this, because the capacitors wouldn't be able to hold enough charge to represent our dynamic range. And what does this look like? Well, it's a clipped signal. It's going to introduce distortion, and we do not want a distorted delayed signal. We want a version of the delayed signal that is exactly like what we put in. So the Compander is going to perform either the compression or the expansion function. And the way that this is all set up here is to do the compression function, okay? It's going to compress our input so that we can't get signals that are so strong that they're going to saturate our BBD, okay? It's going to make sure that we don't get any distortion in our BBD. We're not going to go into the specific configuration of all of these components with the Compander. I don't usually like doing it, but for the sake of how complex this circuit is, we're going to be kind of hand-wavy and say, this is a compressor, that is squishing our signal down before going into our BBDs, okay? Because we don't want to have any clipping. And then on the output, so we take the output through this capacitor, we then are looking at this transistor stage. This should look familiar to you if you have watched the CE2 video. This topology is a third order low pass filter in what is called the Salin key topology. And what it does is it's going to take our input signal and provide an 18 dB per octave roll off above our cutoff frequency. Okay, and so we do this so that we don't accidentally have any high frequency information, which remember, we have boosted our high frequencies a ton over here, so that we don't have any high frequency information that could get aliased in our BBD going into the BBD. This is our anti-aliasing filter, okay? And so once we have filtered it so that we're not going to alias, we then come down to our two delay stages. We have two delay stages that are set up identically here. We have, this is what one of our stages looks like. You can see that our input signal, which comes down here, comes into both of these BBD stages, okay? But we're only going to look at one of them because the other is going to be exactly the same. So we have here our signal going through a resistor, transistor with the collector tied to voltage, 10K resistor to ground, taking signal off the emitter. This is a simple unity gain buffer. It's an emitter follower, okay? And that's going through a DC blocking cap into the input of the BBD chip, okay? And there are these, so the inputs have these trimmer potentiometers that are used for calibrating the unit, okay? We're not going to worry about that right now. If you want to read about the process, it's in the build documentation. The build documentation is actually really great if you want to understand some of the less schematic specific and more kind of overall unit nuts and bolts. So we go onto our input, okay? We've then got the connections for our various power and our clock pulses, and then we have the output, okay? And our output is going to, let me get rid of this real quick so that we can do this. Our output is our pins 7 and 8, which are tied together, and our output comes and does this thing. Why did my pencil all of a sudden go to a skinny little line? Who messed with my line width? I don't know. So anyway, the output from the delay stage comes through here, and now we have this transistor stage, okay? And this transistor stage has a couple of things going on. First, we have voltage. Ooh, that one is way too fat. Now let me get a skinnier one. We come through a resistor and a resistor to ground. These are the same values. So this is setting our bias voltage for the transistor. Okay? So we're biasing our transistor right here. And now let me erase some of my random lines here. And after we bias our transistor, we then have our reconstruction filter. If you don't remember why it's called the reconstruction filter, go visit the CE2 video. But this section right here is our is another low pass filter. It's another third order Salin key low pass filter. Okay? And on the output of that Salin key low pass filter, we are then going to take the signal off of the emitter, so it's unity gain and in phase, and it's going to come into the NE570. But this time, the NE570 is set up as an expander. Okay, it's going to undo the compression that was done by the first Compander that we used. But now you'll see that both sides are connected because the NE570 is a dual Compander device, meaning one half can be set up as a compressor or expander and the other half can be as well. We only used one half earlier in the circuit because we were only dealing with our mono input signal. But now we have two separate delay lines, and each of them are getting expanded to undo the compression after we delay the signal. And so once we have our signals that have been expanded, they come up here. Let's make sure we trace our lines. Here's the output to one of them, and here's the output to the other. Okay? What is happening is that these guys are coming into our summing amplifier. There's the summing amplifier for the left. Here's the summing amplifier for the right. Okay? We don't need to worry about this stuff here. This is all dealing with the jack switching between mono and stereo. We're not going to talk about it. Okay? So let's go ahead and look at these at one of these output stages, okay? Because they are the same. So we're going to come and we're going to look at this guy here, okay? And he also encompasses that, right? Because those are also going to the input. This is our delayed signal in. This is our dry signal in. If the jack switching is done such, this is the other delayed signal in. But we're not going to worry about that right now. That acts as, this is just a solid line for our intents and purposes. So these are our two, possibly three inputs into a summing amplifier. Okay, we're coming in on the inverting terminal, positive terminal is tied to Vref, but you will notice that the way that we have this set up is not like a normal summing amplifier. We have additional filtering happening here. That's because in addition to being our summing amplifier, this is also our de-emphasis filter that provides the high frequency roll-off to undo the high frequency boosting that we did earlier in the circuit. Okay? I mentioned that earlier, so we're just going to kind of breeze through that relatively quick. And then our output goes through a capacitor. There is a pull-down resistor to the output. Okay? So that is our entire audio path, which I can't decide if that seems easier or more difficult than than it seems at first blush. Now that we have gone through and looked at our audio path, let's come look at what happens for the modulation. Okay? So the modulation happens starting with an LFO that is this guy. Okay? This, if you go back and look at the Boss CE2 video and compare them, you will see that these are very, very similar. They're not identical, but they're similar. In fact, lots of things are similar because it's Boss for both of them, and they were both designed, you know, similar-ish in time frame. But this is another trigger integrator LFO topology. Now you'll notice that there are no potentiometers here for rate or depth. The DC-2 has the 4 little radio buttons that you can push, and those determine both the rate and the depth. And so you've got switches that will have, so you have this resistor, but then it can be paralleled. So 330K, it can be paralleled with an 82K, or it can be shorted altogether to change the rate. Okay, these components are controlling the rate. So then we have these resistors on the output that are going to govern the depth of the signal. Okay, and the way that that happens is that if we look just a little downstream, take a little peek ahead, you'll see that we have resistance, inverting terminal, and resistance in the feedback loop. So the way the depth is actually getting controlled is that we are changing the overall resistance seen here and changing the ratio of the resistances between the input resistance and the feedback resistance, which is what governs the gain of this op-amp stage. So we're doing an active gain adjustment of the output of our LFO. So we have a fixed 47K through here, and we have a fixed 33K, which means that we'll never get less than 33K. But we can have this 22K here, which if we have just the 22K and the 33K, that totals to 55K. And our feedback over our input is going to be a little less than 1. Okay? But then with our radio buttons, we can actually change what this resistance is here by paralleling it with either a 470K, a 220K, or shorting it entirely. As we parallel it with resistors, the resistance drops. And when we short it entirely, then what ends up happening is that this becomes a short through here. And so we have the gain of this op-amp stage being determined by 47K over 33K, which is now greater than 1. It's not a huge change in the actual depth of the effect, but it's enough to make a difference. Okay? So there's our LFO. We're not going to talk anymore about it at this point. We're going to talk about what happens downstream from it now. So I'm going to go ahead and do this view. Okay, so here is our LFO signal, right? It has been gained. It's now been buffered as well. And we take that signal and we're going to actually go through a voltage divider to drop a little bit of the level. And then it's going to come and it is going to affect this portion of the circuit, which if we go back to the CE2 video where we talk a little bit more about it, this messes with the oscillating, with how the clock driver chip is oscillating internally. Okay, the clock rate is determined by an oscillator, and that oscillator gets determined by a cap and resistor connected to this chip. But when we take that and we connect it to this circuitry here, it allows us to start messing with how quickly that oscillator is oscillating back and forth inside of the chip, and that's what governs the delay time. And so when we take our LFO signal over to here, we start taking the base delay time that this chip has, that's determined by the resistors and caps, and we start shaking it back and forth to actually change or modulate the delay time, and that's what creates the pitch shifting effect for our chorus. Okay? Now, as I mentioned earlier, the magic of this circuit is that with our two delay lines, they are actually being modulated out of phase, and that gets done here where we come with our LFO signal. We go through a resistor to the inverting terminal of this op-amp. We have the same value resistor in the feedback path, which means that we are inverting the signal here, but keeping the level the same. It's unity gain, but inverting. And once we have inverted the phase of it, we are coming through the same voltage dividers we had over here, and it's going to mess with the oscillator of this clock driver chip the same way. It's just doing the exact same thing 180 degrees out of phase, so that they're perfectly out of phase. That way, whenever this delay chip has an upward pitch shift due to the modulation, this one's going to have a downward pitch shift. And when we sum those signals together, whether it be in stereo or in mono, we still hear that there is pitch shifting happening, but we're not sensing that the pitch shifting is all happening in a single direction at any given time, which is what gives the dimension chorus that more subtle effect, the stationary effect, as it is called. And with that understanding, we have made it through the entire circuit. Okay, so we'll just do a real brief recap here of our circuit. We come in through a buffer. We emphasize the high frequencies here so that we have better high frequency signal to noise ratio inside of our BBD. We compress the signal here so that we don't saturate the BBDs. We apply an anti-aliasing filter so that we don't have any aliasing inside of the BBDs since they're a discrete time device. And then our signal comes down here. It gets delayed here and it gets delayed here. And the outputs of these come into our expander, which is expanding our two signals that then come up here and are getting summed into a left output summing amplifier and a right output summing amplifier, where these summing amplifiers are simultaneously summing the dry and wet signals and undoing the emphasis, the high frequency emphasis that was happening here. Also, I forgot, so let me come back. We're also doing reconstruction filters before the expanding so that we're not keeping any high frequency artifacts inherent in a discrete time signal. And then in order to modulate our delay time, we have an LFO, and that LFO is messing with the driver IC's oscillator so that it's constantly changing its clock frequency. And we do the same thing here, but first we invert it so that it's oscillating out of phase with the one below. Okay? There is our massive but awesome circuit. If you want to see a little bit more modern and flexible implementation of this, go look at my alternate dimension circuit. With newer devices and everything, we can get away with not using companders. We don't have to worry about the BBDs. And it's a really fun effect. It'll allow you to do the classic dimension sounds, but it will also allow you to do just regular stereo chorus or a single voice chorus, and it's a lot of fun. Anyway, I hope you enjoyed the video, long though it may be. If you are not subscribed, I encourage you to do so that you're notified when the next video comes. But until then, thanks for watching, and we'll see you later.